It's 5 past the hour, so let's get going. Um, so today, as I mentioned, we'll be going through the DDPM or denoising diffusion probabilistic models and starting the journey to making the output of those models using the fashion MNIST dataset much better initially. So that will be a journey because we'll revise or implement variations of the DDPM or more advanced papers after DDPM paper came out, and we'll get the output, build the ability to judge whether the output is getting better, but ultimately the judge will be a visual examination of the output and comparing it to the default fashion MNIST data set. So that's kind of the journey we'll be on over the next several sessions of the course. The first thing, just to quickly share, so what we'll start off with is a discussion of the DDPM paper. So, excuse me, some notational quantities as well as the theory of the DDPM paper. We are not going to go through the paper line by line as much as extract the relevant equations from the paper, understand at a very high level the conceptual path that the paper follows, not all of the math, but only the relevant pieces that are important for our implementation. And then we'll jump to the code. And the first implementation will be something that one of the instructors in the course, Tanishq Abraham, implements the DDPM paper. And then I think in a remarkable kind of example of how best to understand and split apart the, what could be a starting implementation and make it better to improve the understanding as the paper gets implemented in easier and easier ways. You kind of see Jeremy implement his version of the paper. And as he does that, he explores the various parameters, the various functions, simplifies the implementation, and gets it to a faster and a better implementation than what Tanishq started off with. So that's going to be the outline that we'll follow today. So the first thing that we need to understand is, there have been many generative modeling techniques prior to what's recently become the norm, which is the diffusion model. And in fact, as discussed in the lecture video, if you watch it, you'll also find out that the diffusion models, the term diffusion itself is something that doesn't always get used, and therefore we're kind of discussing what could be a better terminology. And in a sense, iterative refined models is one of the terms that's suggested. The bottom line in all that is to say, if we provide a number of images of, say, pictures of dogs here used as an example, then the question is, can the process that we follow, whether it is GANs or whether it is variational autoencoders or in this case, diffusion models or iteratively refined models, can they provide a new image of the same class, so a dog, but the reality is that this dog is not necessarily, as we'll see in the future, not in the current discussion, but in the future, not necessarily something that's exactly a replica of the dogs that we see from the images that we have supplied. But to start off with, we'll kind of try and emulate one of or reproduce an image from the data set that we are provided with. So the high-level conceptual overview of the idea is as follows, that if there is an X, which is an image that we obtain, an image of a dog as we saw, from all of the possible images that could exist of anything in the real world, then using some information or some knowledge about the probability distribution of X, therefore the likelihood of X, is potentially helpful to us in regenerating and therefore generative AI, but generating the image of the dog. So that's, a very high level conceptual understanding of what generative models try to do. In other words, if we have some information about the probability of X, then if we sample in that domain or in that space where X is likely to exist, then we are likely to create images in that are either X itself or some likelihood or some something similar to X. As I mentioned, there are many techniques, and more recently, the iteratively refined models have become kind of the norm that's used for this purpose. A simple example that Anish uses to give an idea of why knowing the probability distribution increases the odds of us figuring something out about the image is that of height for, let's say, males in the human population. So think of the distribution of height, or think of the values of heights of males in the population along the x-axis, and the probability that a particular male that's chosen has that height along the vertical or y-axis. So, we all know that height is over a large human population, normally distributed. Therefore, the average, if say, is about 5'10" or so, then you'll see a normally distributed curve. And so this probability distribution then provides us some information. And for example, if we are told that, a high-performing basketball team is chosen from this distribution, then we are likely to kind of search for players who are part of that distribution on the right edge of that distribution, meaning we are likely to find people who are members of the basketball team, given height is an advantage in the playing of basketball. So that's just one simple illustration of how knowing something about the probability distribution can help us get samples from the distribution which are likely to either be exactly that or similar to the population that we are seeking. Okay, that's a very conceptual and a very high level example. Let's kind of dive down in the paper what they talk about with respect to image and the process that we are talking about. So they refer to the process as directed graphical models. Again, as I mentioned, the intent of discussing the theory is more to orient us towards the implementation of the paper. So we'll not be discussing every single line or the all of the math, but understanding the relevant portion so we can code it as needed. So the simple thing we start off with is a clean image. That's the image that you see on the right. And then what we call a forward process is the process of adding noise to the image so that we eventually end up with X at time t. And as we discussed several lectures ago, and this was lecture 9A, I believe, or 9B, and you can go back and listen to that lecture. The links are there in the Slack channel pinned Excel table. But the important thing from there to recall is we will be taking a number of steps. They're called time steps, but they have no relation to time. It is the number of incremental steps that we go through. So X0 is the clean image. We go through a number of steps and we reach X at time t is capital T, which is pure noise because we keep adding noise to the image until the entire image is nothing else but just pure noise. Now, that's the extreme forward process, which means we go from X0 all the way to X capital T. But in order to better understand the process, let's just focus on two time steps, quote unquote, say x at t minus 1 and x at t, where small t, where small t is obviously a time step which is more advanced or incrementally further ahead than t minus 1 in the process of going from a somewhat noisy image to a noisier image. So this image at x at t minus 1 has less noise than the image at x of t. Okay. Now, as is discussed in the paper, this process is a Markov process. That is, it depends only on the image at x of t minus 1 and what we add noise to get to the noisier image at x at t. Right. So the point is that the forward process is a fairly easy one. We just keep adding some amount of noise depending on the time step to the clean image and end up at the noisy, pure noise image at x at capital T. But the denoising process is obviously something that's almost impossible if you just wish to remove all the noise from xt and get back your clean image. Moving on and focusing in on the x at t minus 1 and x at t. However, given that this process is a Markov process, there are closed form equations that describe how to describe the distribution of the noisy image at, or the noisier image at x at t as a function of the less noisy image x at t minus 1, and t minus 1 and t are steps in the quote unquote referred to as time steps in this process. The closed form equation that describes x of t as a function of x of t minus 1 is defined, and this walrus colon followed by equals is it denotes definition. So q x of t given x of t minus 1 is defined as a normal distribution with x of around x of t and with a mean of, and this beta t is some parameter, and there's a mean and then there's a variance. So the beta t is some parameter that determines the amount by which we use the image at x of t minus 1 and the variance. So there is a closed form equation which can tell us what is x of t given our image at x at t minus 1, and that's this, with a normal around x of t and a mean of square root of 1 minus beta t times the image at x of t minus 1, and then a variance of beta t times I. Right? So that's one equation that we'll come back to or use in the implementation of this paper. So as we go from time t minus 1 to steps t, the beta that's in this equation increases. So the bottom line is this important thing that's highlighted here. Beta, the value of beta at t is greater than that at x of t minus 1. So what that means is as we keep adding noise and as we go from x at 0 to x at capital T, the variance of the model, that is beta t, remember beta t is greater than beta t minus 1. So beta at capital T will be much larger than the beta at x1, x2, and so on. Right? And you can think of it very simply by thinking of it this way. Let's consider just close to x0 step or an image at x1. Remember that what this says is the image at x1 is created from the image at x0 because the x1 will be the new xt and x0 is x at t minus 1. So since beta increases, that means the contribution of, so the mean decreases and the variance increases. So that's why as we go from x0 to xt, the noise continues to increase, right? So that means that x1, in a sense, will have a significant contribution to it from the x0. So x1, which is an image which some amount of noise added to the clean image X0 will mostly resemble X0. But as we keep adding noise, the contribution of this guy, the square root of 1 minus beta, beta will keep increasing. And therefore, if we are very close to x sub t, where t is the capital T, then this value will become very small, whereas the variance will be very high, which means that most of the image or all of the image at x sub capital T will become noise, right? So that's one way to think about if you want to kind of think in, what happen as we go through a sequence is to think about the extremes in the sequence. A different way of expressing x at any time steps t as a function not of t minus 1, but as conditional on x0, that is starting with the clean image. And if we want the expression for what is the image at time t, given that at each step we add some amount of noise to the clean image, is given by this equation. And we'll find, in fact, it's given right here that the parameters alpha bar t and 1 minus alpha bar t are, or just alpha bar t is related to beta t, the thing we saw in the prior slide, by this value, that is alpha bar t is equal to 1 minus the cumulative sum of beta t. But what this means, given that we've seen beta t, that is beta value at t, is greater than beta t minus 1, is that alpha bar t will be less than alpha bar t minus 1. There should be a bar here. So the point is beta increases, beta t is greater than beta t minus 1, but alpha bar t is less than alpha bar t minus 1. And if since as t increases, alpha bar t decreases, that means that this value will decrease, and the second value here, 1 minus alpha bar t, will increase. Again, this is similar in concept, and that means that the contribution of x0 towards xt will decrease as t increases, but the variance, that's the noise, will increase as t increases. Okay? So that's what this equation is essentially saying. That's what my notes say here as well. So as t increases, alpha bar, and I've kind of, instead of saying alpha bar sub t, I've just indicated is alpha bar t decreases, so that in the limit, alpha bar t will approach 0, and therefore at x of t, there'll be no contribution from the clean image. It'll all be noise, and that's why here alpha bar t would be the lowest value, which means that this value will be very high. Okay, so the next thing is the important or critical to our backward process, that is also referred to as the sampling process. We'll understand why in a minute as we go through the rest of the discussion. The point is that, as we saw here, going from xt to xt minus 1 to xt is the forward process, and that can be given by this equation. A closed form is obtained through q of xt given xt minus 1, and we saw that in terms of xt, and instead of just xt minus 1 in terms of x0, and that's given by this equation. Now, it's then also possible to define a neural network which is indicated by p of theta, theta being the parameters that we're seeking, to get, this is the reverse process. So we're not adding noise as we go from the right clean image to the noised, fully noised image, but we're removing noise. So we are going from x at, or we're going from x of t to x of t minus 1, or in other words, we're trying to find out what x of t minus 1 would look like given a noisier image at x of t. And that is defined, again, through a closed form as a normal distribution centered around x of t minus 1 with a originally a couple of neural networks, one predicting the mean and the other predicting the variance. The mean with the noisy image x of t and the time steps t provided. And the same thing for the variance as well. But what the DDPN paper simplified compared to prior versions of the denoise diffusion process is to say, let's just assume that, or maybe they even explain the rationale as to why this is justified, but say, let's assume that or define that the variance is a constant that's only dependent on the parameter we have chosen, beta, which in turn depends on the time step t. So given a beta t, it is the constant. So now we just have a single neural network which has to determine the mean. The other thing that the paper does through a variety of mathematical discussions that we did not get into is it basically says that this neural network is equivalent, or the definition for the reverse process, the probability of P of theta, which gives us the x of t minus 1 conditional on the prior, which is x of t, is equivalent to the noise, is equivalent to the loss function defined using a mean square error. And the loss function is of the neural network that we use is given by this equation, where epsilon theta is representative of a neural network. And you see the same closed form that we saw earlier of square root of alpha bar t times x0 plus square root of 1 minus alpha bar t times epsilon, where epsilon is the noise that's added for each time step of t. And that's what we see in the next slide that I pulled out of the discussion. So we have seen that a closed form expression of the noising process, that is for going from x0 to xt, is this guy. And that equation in the paper is shown to be equivalent to a neural network that we train using MSE laws. And I apologize for this being small, but you saw the equation here. That's essentially what is shown, that these two forms are exactly equivalent, where epsilon, the noise that we add to each step in the process to go from a clean image to a fully noisy image, comes from a normal distribution with a mean of 0 and a standard deviation of 1, right? And the other key thing to recognize, and again, we have also discussed this at a very high or in more detail in, I think, 9A or 9B when we started off the course, but obviously we did not get into the implementation details, which we will in a minute in the notebook. So the important thing to understand is the network that we're building, the neural network that we're building, is a noise predictor. So what we do is add some noise to an image and train the network to predict the noise that we have added to the image from when it's provided as an input, the noisy image. That is, a noised image is provided to the network and it's asked to predict the noise that we have added to the clean image. So that's why the network, the neural network that we train, is a noise predicting network. And then we sample from the output of that. After we have trained it, we sample from the same neural network in order to begin to generate the output images that we seek. So the key thing to understand is the neural network that we're training is a noise predictor network. So again, what's a conceptual understanding of what we are attempting to do, or what the diffusion process is attempting to do, is what is shown in this picture. And we'll get to probably a little more detail before we jump to the notebook and look at the actual implementation in code. So here, what is shown is, let's assume that there is some distribution, and obviously we are just showing it in a 2D. In reality, it's high dimensions that the network or the images existed. But obviously, we can't show a 4-dimensional or n-dimensional image. So let's just look at it in 2-dimensional. So let's say that this is the distribution of real images. And what's shown here is that the circle, or whatever the shape is, are where the distribution of real images lie, and outside is just noise or not real images. What we start off with when we train the network, the neural network, the noise predicting network that we're training, is given an image in the distribution, we add some noise to it, and then we try to subtract that noise in order to get it back to the position we started off with, right? So we may start off, for example, from some position that's outside of the distribution, and then the goal is to try to get an image which lies within the distribution. Okay? So that's kind of a very high-level conceptual understanding that we'll refine in a minute. But before that, just the algorithm for training. So what is the algorithm for training? So here are the steps. And while this is the mathematical form, here's an explanation of what each of these steps means when we implement it in code. So this x0 from Q of x0 just says, take a clean image from the data set of images that we have. That's what the first line means. Then the second line says, T sampled from a uniform distribution starting from 1 all the way up to capital T. That again means get a random time step from the set of time steps between 1 and capital P. Then epsilon is sampled from a normal distribution between 0 and I, which essentially says get some noise, which has a value epsilon, from a normal distribution of mean 0 and variance of the identity matrix. Then use the equation which combines x0 and epsilon using the parameter alpha bar, which in turn comes from beta and a time step t, in order to generate a noisy image x of t. So think of what is within this, the first term within these parentheses, which is square root of alpha bar t times x0 plus square root of 1 minus alpha bar t epsilon, as being the noised image x of t. So by combining x0 with some noise, the amount of noise is determined by alpha bar t, which in turn is determined by beta, then and which in turn is determined by the choice of our value of the time step t. This first value is x of t, that is the noised image. We provide the noised image and the time step t to our neural network and ask it to predict the noise that we have just added to the network. So remember, there's 2 steps to the input, 1 step and what with respect to the output, and the output that we're predicting from the neural network that we're training is the noise that we just added to the image to create the noise image at x of t. So what we do is pass in x at t, which is the noise image, and the time step t to the model, and which is represented as epsilon beta. And compared to the target that the network is predicting is the epsilon, is the noise that we have added to the noisy image, or to the clean image, I should say. And that's the actual ground truth noise, epsilon. And then the reverse process, which is the sampling process, we try to get back the actual image from the noise. How do we do that? We do that through the sampling process, but conceptually, this is what is happening. So what we're trying to do, again, referring to a 2D space with this circle representing the actual images, is, see, when we, in the forward process, what we have undergone is starting with an image which is within the distribution, say this dot here, and then we have continued to add the noise. So let's say this is the path we took, and we continue to add the noise, and we ended up at this point outside of the distribution, which is all pure noise. The challenge then is to follow a reverse process which tries to attempt to follow this, but we can't exactly follow this process back to get to the distribution. So what we try to do, and this will become much clearer when we go through the code, but what we do is we start with pure noise. We try to use the equation or the neural network that we've trained to predict the noise at each step to try and predict the noise in this image. But initial prediction of the noise, given even initial value of t, using our trained neural network is not likely to get us back all the way to where we want to go, which is get us the image back in the distribution. So what we do is we take a first step, and unlike in case of the stochastic gradient descent, where, and again, the optimization process we follow is identical to stochastic gradient descent, but the difference is as follows. The difference is that instead of just subtracting a fraction of the gradient that we calculate, which is what we do when we do stochastic gradient descent, because we multiply the gradient by the learning rate. In this case, there's nothing like the equivalent of the learning rate. We just try to completely use all of the gradient and try to subtract that from the image, subtract that being noise from the image. Now, we know the initial value that we get will not, this an iterative process, so the initial value that we'll get from this will not be that great. So what we do then is we start off with a fully noised image, we subtract what we assume is all of the noise, and we get to another point. We try to average, or not exactly, we try to do a weighted average of these 2 points, add a little bit of noise to the weighted average. That determines our new starting point. And we repeat that process again. And by repeatedly doing this thing, or the sequence of steps that I just described, which is start with some noisy image, predict what the noise is in the image, then subtract that from the image, subtract the noise that we have predicted, take a weighted average of those two, add a little bit of noise back to it, get to a new point, again do the same thing, and then through this process of iterative refinement through the gradient, try to get back to the denoised image that we actually want at the end. So that's the theory. Now, with all that theoretical background, let's jump to the actual code. Any questions before we go to the code of what I just explained? I understand that we are not going through every step in the paper, but these are the important concepts from the paper that we will see in the code and that are relevant to the implementation. Any questions at all before we jump into the implementation? Any comments?
Those slides are very helpful.
Okay, thanks. Okay, let's then look at the implementation in code. The interesting part is we'll be using the Mini AI framework in order to implement the paper. And some background about the paper. The original idea of diffusion models came way back in 2015, but then this particular paper called Denoised Diffusion Probabilistic Models by Peter Beal, who runs a lab in Berkeley. And in fact, some of us, I think, were also, we followed the unsupervised learning course, which was a graduate level course that Peter Beal taught at Berkeley. And there are lectures again in Slack that you can go and check out, especially the relevant portions of that which are applicable here are the discussions around VAEs from that course and also GANs. But one particular comment here is the two aspects of diffusion models that will not be touched upon in this particular implementation until we get further down the road are there's no VAE, so there's no latent. Now, that doesn't change the underlying implementation. As we saw very early on in the course, VAE is more of a compression technique. It's used just to compress, if you will, and therefore, from a conceptual standpoint, it doesn't change anything. The other aspect of this that we'll not touch on is the conditional guiding that we do for diffusion models. So there is no conditional. So this is an unconditional DDPM, and DDPM does not use any latent. So those are the two things. The third thing that we'll not spend any time on is the actual unit model that is used by the network to predict the noise. So we're just going to take the model as is, and in a subsequent lecture, 4 or 5 lectures down the road, we will then implement the unit code ourselves. So we are not violating any of the tenets of the class in that we do not, we are using something that we haven't built up from scratch ourselves, but that's only because we will be building it up ourselves in a subsequent lecture of the course. So with those caveats, let's dive into the implementation code of the paper. And the first implementation is something that Tanish does, the instructor Tanish Ibrahim does. And subsequently, we will see Jeremy's implementation, which helps us kind of understand the overall paper implementation and simplifies it, which to me is a remarkable illustration, I believe, of how best to analyze and play with things in order to really gain understanding of the, let's keep going. These are all just set up. So we've done this several times in the course, so that's why I'm not spending any time on it. The one thing though here that you will see is we are resizing the fashion MNIST to be a 32 by 32. And if you run this, you'll see in resized it just a week or a few days back, and had to add this anti-aliasing equals false. Otherwise, it gives a ton of error messages and slows the whole process down. This is, again, stuff that we have done many times before. The interesting thing is because we have set the batch size as 128, you see the shape of XB to be a 1 by 32 by 32 image, and then Y, which is just this fashion MNIST. Keep that in mind. So obviously Y for a fashion MNIST are the labels for what kind of objects these are. This is what a unit model actually looks like. But as I said before, we will not be focusing on this until about 4 or 5 lectures into the course. But very simplistically, it's a model that helps regenerate or generate a very good facsimile of the original input image. And that's done through these cross connections, which we will implement ourselves and understand a lot better as to why those cross connections are needed. And typically, the unit has 2 arms to it, if you will. This is the downsampling part. So each step, as you can see, will increase the number of channels and reduce the height and width of the image. So we go from a 512 by 512 to 368 by 368, and then get that to 284. Again, go increase the number of channels from 64 to 128 to 256 to 512, and in each step we reduce. So this is the downsampling part. The height and width of this reduces in each step until we get here, and then we go back and where the channels reduce and the height and width increase until we are producing an image that's again down to the same number of channels that the original image had and the original height and width of the image. So again, as I would keep repeating, we'll get into the details of this in about 3 or 4 lectures from now of how to implement this ourselves. But it uses all kinds of modern techniques. We will implement every one of those techniques as we go through the next lectures. But here we are just taking the model as is from the diffusers library in Hugging Face. And then the unit 2D model, because our fashion MNIST data has only one channel, not the three channels, which is typical of RGB images. And so our output also is one channel. And then the blockout channels that are given in the default model are these values. That's the model that we're using. What Tanish did is to implement the entire process of DDPM, if you will, in a callback. So remember that the first thing we need to, so here are the steps that is done, and these steps are implemented in the callback as well. So we saw the algorithm in the description that I just went through, right? Now pick a clean image, take a choose a time step, corresponding to the time step, there'll be some noise value, add that noise, you will see all that here. So randomly select the time step, add the noise corresponding to the time step to the original image. And this is, we know this now, that for increasing time steps, the variance of the noise increases. Pass in this noisy image and the time step to a model. So the model gets two inputs, noise image and the time step. And then the model is trained with an MSE loss between the output of the model. Remember, it's a noise predicting model. So the output of the model is an epsilon, that's the noise, and the amount of noise added to the image. So you add the noise, you provide the noise image and the time step C, and you ask the network to predict the epsilon. So that's the target, the epsilon, at time t. Now, the whole thing is implemented in a callback. So the callback will randomly select the time step, create the noisy image before setting up our input, and the ground truth tensor. The ground truth tensor will be the epsilon value for the model forward pass, and then we'll calculate the loss using MSE, right? So this is to be understood that if we randomly pick a time step which is very high, a lot of noise will be added to the model. If you pick a time step which will be small, a small amount of noise will be added to the model. And that's the amount of noise that the model will be asked to predict as well, right? And after training, we need to sample from this model. That's what generates, that's the generative part, and that's what generates the output. So the iterative denoising process, starting from pure noise, is what happens when we sample, right? That is, we simply keep removing the noise predicted by the neural network, but we do it with an expected noise schedule. That's the reverse of the schedule that we use when we added the noise. And the terms like noise schedule and stuff will become much more tangible as we go through. Now, the time step that I'm talking about will obviously have a range, right? So in our current example, we are going to use 1,000 time steps. So that goes from 0 to 999. Right? And so the first thing we do is just go through the code, understand it, and then I'll also share with you the next notebook, or the early part of the next notebook, where Jeremy implements these simple parameters in order to visually understand what they look like. And that gives a much better understanding than just going through the code. But let's go through the code first. So we define a callback. We define the callback to execute. Remember, 0 is the highest priority in callback definitions for us. So the order is the device callback and +1, which means execute this callback after you moved the X and Y or whatever inputs to the device, which means after moving things onto the GPU, then execute this callback. The input to the callback are the number of steps and a beta minimum and a maximum value. So the number of steps is the time steps that we are using, in this case 1,000. Then you get a beta and beta minimum and beta max. The schedule is how you determine the beta, right? And this is just setting it up. Self.beta, and he uses kind of the Greek terms itself. Here in subsequent notebooks, he kind of switches to using the actual self.beta beta. Self.beta is a lid space, and if you haven't seen this, it basically says a linear distribution between the minimum and the maximum values given the number of steps. So it will divide the difference between beta max and beta min into 1,000 values. And that's what the self.beta, therefore, will be a set of 1,000 values between beta min and beta max, all equally divided by the number of steps. And then alpha is 1 minus self of beta, and alpha bar, on the other hand, is the cum product of self.alpha along dimension 0. So this is essentially the definition that we saw of alpha bar is 1 minus the cum sum of beta. And then we also define a sigma, which is the square root of beta. And this is where Jeremy's way of kind of really analyzing what we're implementing comes in really handy. So I'll switch for a minute to show you the example. And these are, I think, some classic ways to really understand what we're implementing and to plot everything, to visualize everything as we go through. So we'll run this code subsequently, or at least go through it because it may take a long time to run. But the point I wanted to show you is he plots the various values, which gives us a visual representation of what it looks like. So the very data that Kanishk uses in the prior notebook is this plot, going from the minimum value 0 to the maximum value, I think, of 0.02 over 1,000 steps. So this is what beta looks like. And this is what a lin space between the min and the max values of beta looks like. Then you plot sigma, which is the square root of, what is sigma? It's the square root of beta. So you just take the square root of these values between 0 and 1,000, and that's what the curve for a sigma looks like. And what does a curve of alpha bar look like? So alpha bar looks like this as we go from 0 to 1,000. And you can see that the shape of alpha bar is as follows. And you can see from these two graphs, what we talked about earlier, that is beta at t is greater than beta at t minus 1. If you use t and t minus 1 as 600 and 400, you can see that. And we also said that alpha bar at t is less than alpha bar at t minus 1. And you can see that here. Right, alpha bar at t is less than alpha bar at t minus 1. Follows that curve. And having these visual examples in front of us really help us kind of get a much more intuitive grasp of what these parameters are and what do they look like as we go from time step t, which is closer to 0, to time step capital T, which is closer to 1,000 or is 1,000. We'll skip this predict for a minute now and just look at how we set up the network and before that. So, this just says from the learner, get the device, which is the GPU, the noise. Now, epsilon is the actual noise that we're adding, and it obviously needs to be added in the shape of our batch. That's the only thing. Otherwise, it's just a random value, and rand n means choose from a random distribution with a mean of 0 and a variance of 1. So that's what we do with epsilon, right? So this epsilon is then x0 is the 0th value of our batch, and therefore is our original image. That's x0. Now we know alpha bar, we move it to the device. We want the batch size. We get that from the shape of our x0, and we choose t. Remember, these are all steps that are aggregated to us that we need to take as part of the algorithm description in this slide. Right, so t is just a random value between 0 and the number of steps, which is 1,000 or 999. And then we choose the batch size, and because we need to take, since we're training in batches, we need to provide the number of steps corresponding to the batch size. And we say alpha bar t, which is this guy alpha bar, we've already figured out and moved it to the device. So alpha bar t, we just reshape it in the same shape as what we need to use. After that, we calculate the noise image, which is xt. And for that, we implement the equation that we've seen before, square root of alpha bar t times x0. And you see that in the equation. This is exactly the implementation of the equation. Square root of alpha bar t times x0 and square root of 1 minus alpha bar t times the epsilon. So you can see a direct correlation between the equation shown in the notebook and the code that we are implementing here and the parameters as we have chosen, and exact implementation of the algorithm that's shared in the slide, which is taken from the paper. Now, the input to our model, as we've seen, is the xt, which is the noise image, the time step t, and the target that we want the network to predict is the noise that we've added epsilon. So that's what our learn.batch is. It's a tuple of inputs, the noised image and the time step corresponding to the noised image, because that determines the time step determines the noise that's added here, and the prediction by the network of the noise. Right? We will discuss the sample later once we get to the training process. So the first thing is set up the batch in order to execute the training. Now, because our network is, because our we have implemented, or Tanish has implemented all of this as a part of the train callback. Now, the train callback has a predict method that can be defined by us, right? And here we need to redefine the predict method for two reasons. The first reason is, so far in our mini AI framework and in our learning framework, when we built our learners, we had a single input as our X input, right? It was just an image. And we were trying to classify the image or do something with it, but the input was just simply XT or X0 or whatever. That's just the image. Here, we have two things that are going into our input, and the two things are XT and a time step T. So it's no longer just a single input, and we need to make that adjustment to provide the model with the two inputs, not just a single input. So how do we do that? Well, we do star learn.batch 0. So this is the modification we are making to the inputs to our learn.model. Reason for the star.learn.batch 0 is because that will then split, or it will separate the input image XFT, that's the noise image, and the time step T. The dot sample, this is the other reason we are having to change the predict, is something that comes from Hugging Face. That Hugging Face API requires us to do, it doesn't just, as with MiniA or something, provide the output from whatever we provide to the model. The output of the model has to be extracted from this attribute sample. So that's the reason that we do these two changes in our predict function of our train callback. Okay, we say learn.pred is learn.model, provide the two inputs and sample from its output. That's actually the prediction. So that's what we need in order to train the model. And we look at the sampling process, which is more of the inference process, once we have trained the model. Right? So the code here we look at once we get. So now we are kind of ready to train the model. Run this. So let's now run that guy. It's going to take a while, but let's keep moving to discuss as it runs. Then obviously we just save the model because it takes a while to run, and we save it and call it a fashion DDPM in a pickle, and then load it back again. Now that we have trained the model with a variety of noise randomly, time steps randomly chosen, noise added, noise image created, noise image with a time step provided to the input, ask it to predict the epsilon, train the model, right? Once that's done, then we go to inference and we kind of sample from the model. Again, the sample function is defined as a callback. The sample function takes two inputs. One is the model itself, that's the unit model that we've used as the noise predicting model, and the size of the output we want. This is the batch size, obviously one channel, height and width. Okay, and then when we sample, as we'll see, we are sampling over the time steps in the model. So the length of the samples or the sampling schedule, and therefore the length of our samples will be generating 1,000 samples. Right. So now let's look as this thing runs to understand the code better of the sampling process. So, so the sample, as I just explained, takes two inputs, the model and the size. The size is the 16, 132, 32 in our case. The model is the unit model that we provide. So the first thing it does is just put the model or move or get the model parameters and move them onto the device. The thing here is, remember, we are now in the inverse process steps. That if we are trying to infer a clean image from the noised image. So we just choose a random x of t, which is of the size that we give it, but again, a random value, rand n, which means random number chosen with a mean of 0 and a variance of 1. So that's what our x of t is, right? So it starts with a pure noise image, nothing like our distribution. So it's a clear out of distribution starting point that we have, and that's x of t. The predicate is a list, and we start doing the iterative refinement process. But obviously, the time step that we want, we are not going in the forward, we are going backward. So we need to reverse the range of number of steps. So here we are going from 1,000, if you will, because we are starting with a random noise, so full noise, complete noise, and then reversing it to get to images which we want to look like the fashion MNIST objects that we have trained the model with. So we start with tbatch dot.full, and you can look at what dot.full is, but it just creates in the shape at given the value t. So that's what the batch is, just creates a batch sized value of that. We'll come to Z in a minute as to why that's relevant. Let's look at the other things first, because Z will become relatable when we get to the appropriate part in the code. The variables, these variables are generated from the beta, alpha, and alpha bar that we used earlier. These are just whatever the equations are. At each time step corresponding to the t that's chosen, we need to determine the direction in which we need to move. So if you recall the picture I had shown of how we would follow the iterative process here, right? So we'll start here and we then keep iterating, right? And that's, we are kind of beginning here. And the direction in which we'll move to get back to the in distribution is what is determined by the parameters in this equation. Okay, so those are the various parameters. Nothing fancy, just an implementation of whatever is our equation, whatever the paper describes. And then what we do is we pass into the model that's being trained the x of t. Remember, in this case, it is pure noise, and t batch, which we have generated here, a batch of t values and corresponding x of t images. So the noised images, which are t value, and we sample from our model, right? So this is, now when we sample, what is the output of this guy? It's basically predictions of noise. These are 1,000 or whatever the t batch number of values that we've chosen, right? It will be that many epsilon values that the model would have predicted. So noise spread is just a prediction of the epsilons corresponding to the noised image and the time in t batch, right? Then what we do is we take x of t and we try to completely remove the noise from it. So this is the process I talked about of not using a learning rate or any kind, completely remove the noise. So that is done through the first part of this equation, right? And if you go back and look at the paper, that equation will be talked about. So it's x of t minus the beta bar of t square root times the noise prediction divided by the self of square root of alpha bar t. So this term, before it's clamped to -1 to 1, is the complete noise that's predicted by the model. And we try to say that's x0 hat. And we define two coefficients which are going to be used to weigh the pieces that we are combining. And one is the x0 coefficient, which is defined by this equation, and an xt coefficient, which is defined by this equation. Again, these are equations which are obtained from the paper, and these are just the values calculated from values that we know of alpha bar and beta bar t. Right? So we have two coefficients, right? And this is the process that I described again in this picture, right? So we can see what we are doing here. Since the initial estimates are not all that accurate, we use some parameters to determine how much we keep of this estimate. This is the weighted averaging that I was talking about. How much do we keep of this estimate of our denoise image, and how much of the original noise image xt, right? So we have two coefficients. We multiply the x0 hat, which is the complete prediction of what the noise is, or the removed noise is. So we say x0 hat times the prediction of x0, I should say, which is the denoised image. And we multiply that by the x0 coefficient. We take the noised image, multiply it by its coefficient, and then we add a small amount of noise to it. The small amount of noise that we add to it depends on the time step t, and this is where the sigma value that we saw earlier is being used. And this is where we use the value z. So z is essentially a small amount of noise that we add in order to the weighted average of the noised image and the denoised image that we get. But we don't immediately conclude that this is a right answer, because what we do is we do this step of combining or obtaining a new xt, and then we go back and repeat the process, right? And this is where also, as we get closer and closer to x0, as our t reduces from 1000 and heads towards 0, you would expect that we will get better at predicting the small amount of noise that's left in the image. And therefore, we would expect that our x0 coefficient will become higher and our xt coefficient will become lower. This is exactly the reverse of what happened when we went from x0 and headed towards x of capital T. As we do the reverse inversion process, initially we will weigh the x0 coefficient small amount, because we realize that our initial estimates are going to be wrong. But as we get closer and closer in t towards the end of the process, that is, as we get closer and closer to x0, the original image that we want to extract through the inference process, the amount of noise that's left to be extracted is small. We expect the image to be closer to x0. Therefore, we make x0 coefficient high and we make xt coefficient low. And if you look at the map here and figure out how these values are changing as t decreases, or in this case, because we are proceeding from 1000 to 0, keep that in mind because it's reversed, then we'll find that this corresponds to what I just told you, right? That's essentially the description here. We append for each step that we go through the predictions and return the price. So that's what the sampling process does, which is where the inverse process. So the before batch in the callback helps us set up the network, if you will, and our model to do the training. The sampling is the inference process. Any questions? Because that's the crux of implementing the GDPM paper.
There's a bit of complicated math involved in this.
Sorry, mine couldn't hear you clearly.
There's a bit of advanced mathematics involved in this.
Yeah, I mean, if you get to the underlying reasons for why the equations are the way they are, and want to kind of purely grasp it, there are tutorials and stuff that explain it. But at a high level, if you are interested in the implementation, I think understanding the process and what you are trying to do with the process, I think is good enough to get the implementation done without knowing all the nitty-gritty details of why the coefficients are the way they are and why this process works.
Mm-hmm.
Right. So let's see. We trained the network. We haven't saved it yet. Let's do that, and then let's kind of sample. So obviously, because it is generating 1,000 samples, it's going to take a little bit of time. But here's the interesting part. What we are interested in is the last sample that it generates, right? Because remember that it's generating 1,000 samples. And what we are interested in is in figuring out the very last step, that is as close to X0 as you can get, and what is the image that it's generated. So then we do the show images. That's why the samples at -1 then gives us the last of the 1,000 prediction. And what these outputs are the generative outputs. So we started off with pure noise, and we have ended up with samples which are very close, if not really good, images of our fashion MNIST images, right? So we started with complete noise, but we've ended up with images which are within the distribution of fashion MNIST, if you will, right? The next thing he does, or Tanish does, is to simply kind of examine or create a plot through animation of what are what is the process we follow, because this sampling process is fairly it's not slightly deterministic, but it at least is, through the code we can kind of understand or show the images as we build the prediction, because there are 1,000 of them, so we could just sample them and show what those images look like as we go through the 1,000 steps. So that's what he does here. So let's pick, instead of all these, how much ever 20 images, let's just pick, I think he picks the 9th index or the 10th image. That's the 9th index, so the 10th image. And then he plots every 5 time steps between 800 and 990. Remember, we are going from 0 to 1,000. So in effect, we are plotting between for these 190 steps every fifth, and then every one between the last 10, and then for the last we plot 10 time steps. So they're just kind of focusing in, if you will, on the last 100 or so time steps. And if I think I've already done that. So you can kind of see this plot of the shirt, this guy, is our 10th image, and how from complete noise, it begins to emerge slowly, go through the steps. Now, here is something else that we'll play around with a lot more as we go through the remainder of the notebooks. But here, he's just focused on 800 to 1,000. Why? Because as we'll see in the next notebook that Jeremy works through, most of the earlier steps are essentially noise, right? The previous steps are all quite noisy. That's because of the kind of the noise schedule that we have followed. And there are subsequent papers, as I mentioned, beyond DDPM, called Improved DDPM and DDPI as well, instead of DDPM, which will give us a much better noise schedule, and therefore a much better kind of more utilization of the time steps that we have, and so on. So we could also, one of the exercises is to change the noise schedule. By noise schedule is meant the data that we added. So it's this guy, this is the noise schedule. And we have used a linear noise schedule. There can be a cosine noise schedule, which we ourselves will implement. And those kinds of things help us get a better result from the denoising process. So that's essentially, and a noise schedule is basically how a beta is defined, and how a beta is defined determines the sigma and the beta and the alpha bar, as we saw from the equations, right? So the next set of notebooks that we are going to, the next journey that we are on is we saw this as being our output, but these are okay, but not that great. We have kind of reproduced. Remember, we tried to do the same thing with a VAE back, I forget in which lecture, and we got really poor results. These results look a lot better than just the outputs we got from an autoencoder. At that time, obviously, we didn't know how to initialize a network, how to train it, how to use ResNets, how to do convolution, all of those kinds of things. Obviously, if we had done all that, maybe with a VAE, it would have been better, or actually just an AE or an autoencoder. But here, we are getting a much better result. The goal over the next several notebooks, not the immediate next one, because there we take a diversion to kind of understand the many uses of mini AI. But after that, the next several notebooks will be focused on making the output of our generation process to generate fashion MNIST as good as our original images, which were the plot. If I believe we have a plot at the very beginning. Well, we have it in the next notebook. Okay, so now let's go to a simpler implementation of the entire process. Again, it's the re-implementation of DDPM, but we will be focusing on implementing it, but understanding the paper and thereby kind of pulling apart the pieces and then putting them together in a much simpler way. But before we go there, any questions?
Yeah, if the model is off in a particular prediction, like, will it end up generating something that looks like a different image? Like a different article?
I don't think it would be a different article as much as it will be a noisy version or not a well denoised version, if you will. Give me just a second. Sorry, I have a disturbance that I need to tend to. Just a minute. Back. Okay, back. Sorry about that. To answer your question, Emily, I don't think that it would generate a different object as much as probably a not faithful illustration of the image that it's generating. So it will be just noise or not well denoised image. And you can play with it yourself to see what happens.
Okay, thanks.
Okay, so let's look at this. I think in the interest of time, I'm not going to run this notebook because it takes a while. But I'll go through the code and you can run it yourself. I did do that. As we saw what he does initially, here's a plot of the original MNIST data. So you can compare that.
You have not shared your screen yet.
Oh, sorry. See it now?
Yeah.
Okay, so we saw this is what the denoised images look like, right? And this is what the original fashion MNIST look like. So as you can see, long way to go to get these images back to S. Let's look at the boot, for example. Boot, you can see kind of a symbol here, probably the Nike symbol of that. With this t-shirt, you can see some of the stuff. I mean, still not that great because these are just 32 by 32 images, but you can see some texture, you can see some folds here, things like that, but you don't see any of that in these images. It's pretty poor, right? So that's why he says, hey, I like everything visual. I want to see what I'm looking at. So here's the original image, much more detail, right? And then here's what he does. He takes the code out, pulls it out from the paper, just plots each of them. Again, a very good habit to develop of if you're using parameters, things that try to visualize what they look like. This is what it looks like. Beta, the sigma, which is square root of beta, and the alpha bar. Right? Now, again, yet another simplification in order to be able to play with it. Let's take the code from the from the before batch portion of our stuff here, before batch, which was used to build a model where he used the training, right? This is the implementation of the training algorithm, this guy. So let's just say, define this in a function and implement that. So noisify, provide a clean image, alpha bar. You could potentially have said, time step and from that generated, but he's chosen to give in the input as alpha bar to noisify. So noisify just does the generation of the inputs ready to be supplied to our model. So, these steps are kind of fairly self-explanatory, but as it goes through them, you just define the time step, add the noise corresponding to the shape, alpha bar t from alpha bar, reshape it to the shape we want it, and then do the xt, right, which is some amount of x0 and some amount of noise. And then the xt image, the t, we haven't moved t to the device, but xt is on the device, and then epsilon, the label that we want to predict. Now, here's again something that he does, which I think is really useful. Let's say we noisify the first 25 inputs. Remember that X batch can be, if a batch is 128, we can choose 120. But he says, let's keep it simple. Let's say 25 images. Provide alpha bar. Alpha bar obviously has a corresponding time choice. And when we do this, obviously what we will get as an output is the noised image, the time step, and epsilon, right? So that's what we're getting. And if we then print the time step t, let's say these are the randomly chosen because we've been randomly chosen. So let's say these are the randomly chosen time steps. Then he just does a simple titling of the image corresponding, because these are the noised images xt, right? So xt at t, you can just stick t as a label, and he uses the extended map. You can go look it up from the FC library, fast core library. It just basically uses the format and makes t a string. So the time step, which is actually an integer, becomes a string and can now be used as a label. And these are the noised images that are these are the noised images corresponding to the time step t for the first 25 inputs to our batch, right? And we have chosen t randomly. So you can see here that obviously when t is 0, you're getting the image as is, right? No noise added to it. But as t is 82, we can kind of see still that the shoe is what is the image that we have had noise added to it. Here you can vaguely see this yet again a shoe or a kind of a shoe. But as we go anything about, and you can see maybe it's this shirt or potentially even this, but I think it's a shirt, a t-shirt at about 187. So by the time you get anywhere close to, I don't know, even 202, you can't really tell what this is. But anything above, I don't know, 250, even for a 177, I'm hard pushed to say what this is. Okay? But anything in the 200 plus, 336, 6, I mean, there's no way I can tell what this is. But this is a good illustration, and this is what I meant earlier when I was answering UMG, that you could potentially plot the time steps for a particular image and see what the amount of noise that you added in, how much of the image exists or doesn't exist. Because so much noise has been added that day, right? And he just like he turned the batch function or the before batch function into a noise before batch setup of the callback into just a simple noisify function. So he also does the same with sample. So you just define sample, and obviously with a decorator of no grad because you're not wanting to train the model. This is an inference. So here the inputs that he chooses are model and size, and then all the parameters as well. So alpha, alpha bar, sigma, and the number of steps. And again, because we've gone through the code, it's very self-explanatory, but basically the batch is generating the time steps in a batch corresponding to the size of the batch. Then you generate the Z. Remember, Z is the small amount of noise that we add at the end, which is used with sigma. Then you just calculate the values, and then you do the X0 hat, which is the thing that tries to predict using the network the noise, and up to here, I should say, and then combines it to produce XT, appends it, and returns the threads. And then that's sample converted to a function which returns the thread, right? So before batch is just noisify, and the sample method has also been converted to a simple function. So by converting these two into fairly simple functions with whatever set of inputs, you kind of, the other thing which you learn by doing this is what set of values do you need to provide to it in order to be allowed to calculate, right? You can see that noisify just requires X0. You could even conceivably say T because T is generate, but anyway, alpha bar and X0 is what he chooses. And model size, and then the various alpha bar, and sigma, and the number of steps is what he chooses for the sample. And then now the callback becomes very simple. So this is, in effect, just different ways of playing with the mini-AF framework and simplifying the paper implementation, right? So now our before batch is nothing but just noisify this and give it the alpha bar quantity which you've calculated here. The sample is nothing but returning the sample function with these values passed into it, right? Now, the other thing he does is, let's say, we did not, one thing I failed to highlight is in the prior implementation, and this is where having some understanding of the mini-AF framework, the learner, and the callbacks becomes important. The earlier implementation of the TDPM callback, it was a train callback. And because it was a training callback, it allowed us the ability to redefine the predict function, which is what allowed us to supply two inputs instead of the traditional learner usage of single input going into the model, right? But in this instance, he wanted to simplify. In fact, he just wants to illustrate different ways that you can do things using mini AI. So let's say we simplify the callback because we have simplified the DDPM callback using the two functions. So we don't want to use train callback, but just use callback. Now we are left with a challenge because our learner expects single input or the model expects a single input. How do we now provide two inputs to the model? Right? We are left with that challenge because we can't redefine predict because this is not a train callback. It's just a simple callback. So given that, he says, here's another way that you can accomplish the same thing. You just redefine, you define a new model called UNet, inherit from the UNet 2D model, and redefine the forward of the UNet function, or not function, the UNet model that you have defined to accept multiple inputs. Because the forward of a model, UNet 2D model is an NN model. So the forward of UNet can be defined in the class UNet that you define. And that forward replaces the forward of UNet 2D model. And there you just say, hey, use the super says use this forward function, but define it and provide two inputs, and also solve the Hugging Face problem of need to add dot sample to get the outputs of the model. So this is yet another way to create the same set of learners. Now you've solved the problem of the model requiring two inputs using your own UNet, and you have kind of simplified the callback. So now you can define the DDPM callback to be the number of steps, the beta minimum and beta max, and then we reuse the UNet class that we've just redefined. And here he again is playing with the various values. So he says, I wanted to make this process a little bit faster than what Tanishq had done, which is use the blockout channels that were given by the original UNet model used in the diffusers. Now, if you look at that model of UNet, I think it's for this, yeah. So the blockout channels there are 32, 64, 128, and 128. So that's what is used in the UNet model, right? Now, he says fashion MNIST is a fairly small data set. The images are only 32 by 32. So do we need this number of channels, or can we reduce them? So he tries to reduce them. You can see that instead of going 32, 64, 128, 128, he's divided each of them by 2. But this is where, as you play with things, you also might encounter problems. So he says that when he reduced this, he found out that, oh, wait, the original UNet 2D model used group norm. And if you are forgotten what group norm is, it's the norming, but with certain number of channels combined as groups instead of all the channels. And so that's apparently implemented in the basic UNet 2D model of the diffusers. And you run into problem because there aren't, when you do this, there aren't enough channels to group, especially in the low channel count portions. And so he had to reduce the norm groups to 8. Apparently the original norm groups were 32 or something. And obviously if you're using you can split 16 things into 32 groups. So he had to kind of add this because he reduced the number of channels, and this was done in order to see whether he could. And he implements that, does a fit. Now, again, one of the advantages for mini AI is you can fit, but not really, meaning you don't run the entire fit. You just do a single batch callback in order to just generate the noise, right? Or the noise images. So you're not actually training, you're just kind of setting up the inputs. And you can do that in the mini AI framework by just calling fit, but without training, right? And so basically it just generates a batch, and from the batch you extract these values, and then you do the show images with them. I hope what he's doing here is clear. Any questions? If not, again, he plots them, and you can again see what I had illustrated earlier, or what I discussed earlier, which is when the number, this is the label, this is the time step, and the time step is small, you can see the image because there's less noise added to it. So this is, time step TF6. You've added only noise corresponding to about this here in alpha bar, if you will, or here in data, somewhere here, very early on, less amount of noise, right? So you can see much of X0, but you can see most of the image, even as low as 234 is completely gone. And obviously when it's at 800 or 900, and again, this is a forward process, right? So you're adding noise, not subtracting it. So you can see that none of the other things have any chance of recognizing what the heck the image is. 293, okay. At 98, a little bit for sure. 104 can still make out. That's a shoe of some kind, but anything beyond, even at 186, maybe faintly, but that's it. Everything else is a bonus. Okay, and then he wanted to train with a faster, or train the whole network faster. So he wants a higher LR. What he found out is, and this is a kind of interesting observation or comment about the details that we have learned in the course as well, that even in a paper like DDPM, they have not used anything other than the PyTorch defaults to initialize anything, right? Now, we've seen, as we went to the code, that our init values really help. Initializing networks with the proper values really helps. Can converge faster, give better results, give better generalization results, and so on and so forth, right? So PyTorch defaults are definitely not the best. So what he does is he kind of trains these, but he then subsequently resorts, after a bunch of conversations with the people who actually have implemented this or are experts in the whole diffusion image generation and diffusion paper implementations, or have written papers, I published many times on these models. He kind of discussed the various things or various steps that he could take to improve initialization. So what are those steps? Those are done here in this portion of the code with the init DTPM of the model. So the unit model gets initialized better for DDPM. And some of the things he does is stuff we have discussed before, that is take every second convolutional layer and zero it out. That is, when in a RESTnet, we had this two-step convolution, right? The first bit goes from NI to NF, the second goes from NF to NF. He takes the second one and then zeroes it out. Of course, he does that in the UNet, and we will look at the actual implementation of UNet that we do ourselves. But here, think of it as, again, basically zeroing out some portions of the weights of the convolutional layer. It could be done using backnorm, which is kind of what we tried very initially. But the goal of this is if you recall, in any residual network, there's a residual path and then there's a path through the convolution. You want the path through the convolution to be generating as close to the original image as possible initially, because you know that you're not training the network, so your output is likely to be highly non-useful. So essentially, what this initialization does of doing the second convolution and zeroing it out, if it makes the non-ID path in the RESTnet do nothing in the beginning until the convolutional weights are trained. You want them to generate output which are close to nothing, so that the ID path dominates, right? Then we haven't discussed much of what is orthogonal weights, but essentially this is orthogonal weights that, so by the way, corresponding to the code, this is what he does. So for P in O.RESTnet, P.conto weight data 0 basically says make the weights of the convolutional neural nets, the second part 0. And then he says also for P in the downsamplers, that is in the downward path of the unit, the path that I showed you earlier on the left side of the unit image, make those to be orthogonal weights. And we haven't discussed what orthogonal weights are. You can go look it up in any linear algebra course, but using orthogonal weights for the downsamplers also was apparently a good idea. And in the up blocks are the blocks that you use for going up the right side of the image of the unit, which you are trying to increase the size of the image. And that is something else that zeroing out the weights of the very last layer is also used, so that the neural network starts by predicting 0 as the noise. So when its initial prediction, again, of the entire neural network will probably be wrong. So you start off by predicting, I don't know what the noise is, which is 0, right? And those are the 3 steps that are implemented here. Right, the initialization, which and you execute any DTPM on the model. The last thing he highlights, kindly enough, these kinds of details, deep learning is still a very empirical science in which most people will tell you we've worked on it, is try it, because there isn't a single answer of whether something will work or won't work. And keeping with that kind of mindset, he finds that yet another thing that the DTPM paper at least does is it uses the default values from PyTorch of the normal Adam optimizer. For what? For the EPS. Now, EPS, if you recall, and we went through the details of the Adam implementation and the Adam code, is the not in the momentum, but in the I forget what the second part where we use the square of the gradient. There we use EPS to divide in order to keep the value from dividing by 0. And that EPS is the very small quantity that is used. That quantity, the default PyTorch quantity is 1e-8, right? But that's so small that it still results in a very significant uptake, which is not what we want. So if that EPS is increased from the default value of 1e-5 to 1e-8 to 1e-5, that seems to have a positive impact on the learning rate, and that in turn has a positive impact on the overall gradients not exploding. So you can kind of see that value of these small things like initialization, like not using the default EPS, but increasing it to 1e-5 in the op function. These kinds of things seem to have a big impact on the training. And then he does the learner trains the network and saves the model, and then goes through and samples and shows the images. And you can see that these are, I think, a lot better. I don't know how much, lot is a very qualitative term, but still, if you look at, sorry, wrong. Here, this is what we got from Tanishq's implementation. This is what we're getting after after initializing the network better, using a better learning rate, or actually a better EPS in the optimization function, I should say. You get these, and at least I would tend to argue that these are quite a bit better than the generated image. The next set of things that he does is get into using mixed precision. So precision of floating points and stuff. There's a whole set of links that I can provide on the details, but suffice it to say that what we are using currently is 32-bit precision for representing floating point numbers, also known as single precision. And that uses a lot, obviously that uses the entire 32 bits of the value in order to determine the precise value of floating point numbers used in the calculation. If instead of 32-bit, you could use 16-bit precision, obviously you are not as precise in the values that you're calculating using the floating point version of FP16, but that's good enough from the standpoint of the results that you're seeking to implement as part of this process. And obviously, because you're using 16-bit as compared to 32-bit, you can imagine that you can process a lot more of code in the same amount of time, right? So the computation with GPUs is much, much faster. But 16-bit obviously do not represent the same range and the same with the in precision the values, and therefore they provide a speed advantage, but they may be inaccurate. But the question is, depending on which portion of the calculations you want to use the precision, reduce precision, you can regain a lot of the accuracy that's lost, or another way of stating it is you can minimize the loss in accuracy if you're careful about where you use reduced precision, right? So we try and cover, we have about 15 minutes, we try and cover as much of the mixed precision because actually he covers this in the beginning of the subsequent notebook, but since or the beginning of the next lecture, but because there's substantial amount of material to cover in that lecture as well, I'll keep going and see how far we get. We increase the batch size, and we'll get into later discussion. I'll explain why the increased batch size, but the important thing is that we are using mixed precision. But before we use mixed precision, in the classic sense of Jeremy kind of trying to further simplify, further improve, he's constantly tweaking things in order to improve them. By improvement can be in the form of simplification or in the form of speed or performance, right? So one of the things he says is, wait, I can kind of get rid of the DTPM callback completely. And the way to do that is, remember the DTPM callback did two things. One, it provided the noisify, and the other was it gave the sample. Now we converted both of those to functions. One of the way we can get rid of the callback is we can put noisify inside a collate function. The collate function, if you recall, we use default collate from PyTorch. It's a basic function which takes the image and converts it into the tensors and kind of combines the tensors, right? So that's what we do in the collate. But if we use the default collate and apply noisify to the output of the default collate, then we could thereby eliminate the need for noisify within the callback. So he just applies the noisify function to the output of the default collate of a batch. And obviously we take the X value from it because it's the image that we want to noisify. And then a noisify function gets obviously the X image and alpha bar as we've seen before. Right? So it takes each row of the data of tuples, converts it to tensor, one tensor representing independent, another the dependent, right? And the default collate is, so we pass the batch, grab the X, noisify, and exactly does what the before batch did. Then we create a DDPM loader. What does the DDPM loader do? It just takes the data loader from the data set, provided the batch size, uses our DDPM collate or collate DDPM function, and then does it over the number of CPUs that we got. Right? Then we use the DLS, and instead of from DLS or .dls, you do the traditional data loader thing of providing the data sets, the training and the validation data sets. Then he, in keeping with the process that we have followed of always implementing the stuff ourselves, if you go look at, if you do a Google search for PyTorch mixed precision, you will search for mixed precision. You look at that, it says, here's what you do. You define a scalar, and then you do with AutoCast this device, and then you do the strings, and then you do scalar.scale of the loss, and then scalar.step, and then scalar update and stuff. So that's what is defined when you do a mixed precision training, which means you want to use 16-bit precision when appropriate. And so here, before fit, he implements a callback, uses a training callback for that. And before we fit, we want to define the scalar, exactly as what I just showed you. And then we define a context manager. So before a batch, you set the AutoCast. That's the thing that you saw in the stuff here with AutoCAD. So that's context manager. So here we just set the context manager to be before batch. And remember, a context manager is enter and exit. So before batch, set the context manager to be our port 16. After loss, exit it, right? So that's the period before we do a batch, and after loss, that's the intervening period in which we want to use it. And then when we do backward, we need to follow what Python tells us to do. Same thing with step. We have to use the scalar instead of just doing opt-out step. So this is just an implementation of what has been suggested to us by the CUDA code. And one of the reasons we increase the batch size is as you reduce the precision, the GPU can do much more work, right? So in each step, the GPU now has half the data, roughly speaking, because you're processing in 16-bit chunks instead of 32-bit chunks. Not exactly, because depending on which portion of the process, we may still retain the 32-bit precision. But be that as it may, all that is hidden underneath the scalar or behind the scalar. So we just increase the batch size by 4x because fashion MNIST is such a small data set. Now, when we increase the batch size by 4x, what happens is we have 4 times less opportunity to update the corresponding parameters, right? Because we'll have 4x less batches. So 4 times less opportunity. That could be a problem to get as good results as what we saw earlier. So in order to make up for that, he increases the learning rate from what it used to be, which was 5 in X3 to about 1 in X2, and increases the number of epochs, a little more of training. So he changes epochs from 5 to 8, changes the learning rate from 5 in X3 to 1 in X2, and obviously with all of the proper initialization, blah, 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 he just trains the model. He gets to a better value of the loss, and he plots, and you get, maybe not as great, but still better than what we saw in the default implementation that Tanishq had. So that's kind of what he gets with the mixed precision implementation. There is even better and an even simpler way to implement mixed precision, that is by using the accelerate module of Hugging Face. And he does that and a few other changes in the code, which let's see whether we can cover it in the 5 minutes left. You import the accelerate module and import accelerator. And the way you use the accelerator is to say, hey, I want a mixed precision. Again, define it in the train callback, accelerate callback. Here he defines the number of inputs passed into the accelerate callback, define an accelerator as self.act. And the way to use an accelerator is you call the accelerator and you say prepare, and you pass in the model, the optimizer, the data loaders, the train and the validator loaders, and the accelerator returns the mixed precision versions, quote unquote, of TUIs. So you get the model, the optimizer, the data loaders. And in the backward, you need to also say self.act.backward instead of self.backward, and then pass in the loss. He again continues to fiddle around with the various values. Instead of returning a tuple and a value, so instead of returning a tuple and a value, which is 2 values, he flattens the tuple and returns 3 values, which is the xt, the t, and the noise. So that, now given that you have changed this, we'll also need to change the input passed in to the learner, right? Because the learner now, instead of getting 2 things and then learn.batch, star learn.batch, which is what we saw, in order to accommodate the fact that the inputs are 2, and now it's flattened. So when we pass in the input to the model somehow has to know that, hey, the first 2 things passed into me are inputs, and the last thing is the target or the label, the output that I want to generate. So how do you do that? He does that by actually changing the learner. And that, if you saw, and I'm now switching to the 14 augment notebook, I will go to the process process where we saw the modification in the learner. I think it is this, but if I don't find it, I don't want to spend time. And the point is, he adds n input to the learner, and therefore we are now able to say star for until n input, and all those would be considered as inputs, and then star n input to the end of whatever you provide, so that we are able to split whatever numbers this is. You could even provide 5 values here and tell it, depending on n input, of where to split in order to consider everything before that as input and everything after that as target. So you could have 3 input, 2 targets, or whatever you want to provide to the model. Now, having done these changes, the only thing left to do in the callback is to simply support the Hugging Face change, which is to say you need to add dot sample. Everything else remains the same, and he trains this, and even though he's training it for 8 epochs, he finds that you can train it twice as fast because you're doing it with the reduced precision and so on, and that's kind of the value of using mixed precision. I think I'll stop here. I might take a few minutes to describe what he calls as a sneaky trick, not relevant to the discussion here. It's something that's more useful in Kaggle, so not material to our current discussion. Any questions before we hang up? A lot that we covered, but I would encourage all of you to play with it and get familiar. We will be on a significant journey after the next discussion on trying to implement varieties or improve the whole implementation of the iterative refinement or different model inference. So Rishabh, the notebooks are all there in the, if you follow along with the Fast AI course links, they're provided. I think I provided the very early, it's I think pinned to the Slack channel. These notebooks that I use, I comment heavily. If you're interested in that, I can provide a link, let me know. But the default notebooks that Jeremy uses are all available on the Fast AI website. Any other questions? If not, thanks for joining us. See you all next week.